So, a very good evening to all of you. We hope you've had a good beginning to your weekend. And we are also pretty sure that you'll have an even better part of the weekend in the next 1.5 hours to go. So, welcome to the 25th talk of Varahamira Science Forum, which is brought to you by Varahamira Science Forum, as well as Tamil Heritage Trust and the Tamil Virtual Academy. Before we get into the talk, a few program notes before about the three different organizations, an introduction to the speaker, and then we will have the formal talk. So we will first start off with the Tamil Virtual Academy. They are an organization, they are a part of the Tamil Nadu government, and they've been around for many years. They've done a lot of service, in fact, excellent service in terms of putting together content and holding content about Tamil literature, art, architecture, and a lot of other things. They are a treasure trove of books. They are a treasure trove of content itself related to Tamil. Their website is www.tamilvu.org. So they've been, I think, holding a series of talks of their own once a month. And it is definitely, I think, recommended and worthwhile to go to their website once in a while to look at whatever is new and whatever has been brought out by them as a latest publication. The Tamil Heritage Trust, the THT, has also been an organization which has been around for more than 10 years. It is a completely volunteer-run organization, fully not-for-profit, so we do not have any allegiances or alliances with any other organizations. We are standalone. We also run completely on volunteer effort and with minimal funding from outside as much as possible, though we do now take funding as and when for bigger programs. We have a monthly series of lectures which has covered science, art, architecture, Muslim architecture, Hindu architecture, the study of Jains, Buddhists, etc. We've had a bunch of speakers which have included the likes of Villanur Ramchandran, Professor Dayanandan. We've had our own Gopu and a bunch of other speakers who've been speaking there. Professor Swaminathan, who's here with us in the audience, is the founder and the and whose brainchild Tamil Heritage Trust is. So we've been fortunate to have some of the cutting-edge speakers talk about their fields, etc. As part of that, a group of people within the Tamil Heritage Trust sat down one fine day, and said, you know what, there is something which is missing in the Madras scene here. And what is that? So that is science lectures. So then the question automatically comes saying, no, the Anna University holds science lectures, the Birla Planetarium holds science lectures, IIT holds science lectures by the dozen. You see notifications coming on your phone almost every day. But what is different? What do we want? So the aim, I believe, and the best way to summarize what Varahamira Science Forum is trying to do is not to bring the cutting-edge speakers from the leading institutions of the country, though if we do have them, it's a great pleasure. It is not also to take topics that are right now at the cutting edge of science, but rather I think the focus has been to take science concepts and have speakers who can bring it down to a level that any person who's interested in science, common man interested in science, is able to grasp the concept itself. And I think therefore we've had the ability, and I think we've succeeded so far in having multiple talks on a variety of subjects. We started with Gopu talking on Antoine Lavoisier, the father of modern chemistry. We then had Badri Seshadri talking about the triple helix and the Madras connection, which is Dr. Ramchandran of the CLRI. We incidentally also have an auditorium there called the Triple Helix Auditorium. The third talk was actually about a very interesting part of biology, which is bacteriophages, where we had a very young speaker, Shivaraman, who actually spoke about this. He's a popular blogger. He also gives a lot of talks, a lot of training sessions. A fourth talk, there was another enterprising youngster called Siddharth, who actually gave a talk about Principia Mathematica, and Newton. Actually, you know what? It sounds nice to talk about oneself in third person. But yeah. Then we had a bunch of other talks, including we had Aladi Krishnaswamy talking about his father and the founding of math science. We had Dr. Villanur Ramchandran giving not one, but two consecutive talks for us. We had an introduction to Venki Ramakrishna and his discovery of RNA and the ribosome. We also had we had a bunch of talks, including wandering coastlines, about rivers, about rain. We had a talk that spoke about the Periyar Dam and Peniquick. We have the speaker here. In fact, we've had talks on a whole variety of topics. We had a woman talking about the women scientists in India, Dr. Uttara Dorairajan, who I don't see in the audience today. We have a bunch of topics that we have put together. I think we have had an eclectic series of talks. This started off as a seed of idea to try to get talks out. And we are proud to say that we have crossed 2 years and we are still running strong. We have an auditorium.
We are completing 2 years today. Next lecture will be the 3rd year.
Okay. So we are completing 2 years today. This is the 25th lecture, which means we've done 2 years today. So we have completed 2 years. And
2017 we started. So next month will be the 3rd year we are stepping into.
So there you have it. That will be the 3rd year we are stepping into. And we are stepping into it strong. We don't have a shortage of speakers. We have people who are interested. One of the biggest signs, I think, that Varahamihira Science Forum is flourishing is we do not look for speakers. We have many speakers who come and tell us we would like to speak. And I think that talks more about the success of an organization than anything else. We've also been able to host a bunch of workshops. So I did a workshop in the last year, which was focused on bringing science through a hands-on experience to children. We did it as a part of 2 days. We had Gopu talking about Indian mathematics and astronomy, looking at the history of it. It was so successful that a bunch of people came back. This was actually for children last year. A bunch of people came back and said, why do you have it only for children and we'd like to have it for adults? So this year, on popular request, Gopu did an encore, but for adults. But moving on towards where we were as of last month, we had a very, very interesting and a very thought-provoking lecture, which actually tingled our axons on the history of neuroscience. And we have the speaker, Nishant Chandrasekhar, here with us. And I think one of the biggest ways to connect this to our talk today is we have had, and I think this is a great achievement, that we have had two flautists who are speaking back to back. So Nishant plays the flute, we have Aakaash who plays the flute. And for all of you who are new, this is Aakaash's second talk. Earlier, he had given a very, very exciting topic called Atomic Theory for Alamelu Party, which was to tell you that atomic theory in a language that Alamelu Party could actually understand it. Now, he's taken that one step further and he said, I'd like to look at the history of light and talk about the story itself of light itself. And I'd leave the intricacies and the details to Aakaash. But Aakaash is one of the really brainy people I know. He is doing his research. I don't want to get into his research as much as the amount of eclectic things that he does. At one point, I should tell you that many of Ilayaraja's hits I kind of got back, because you would see a video of Aakaash switching on the camera, pulling out his flute and playing one song for you. And between all of this, he's got enough mental acumen, capability, and just the drive to pursue his research in physics. And if that is not enough, for the next 1.5 hours, he will show you what a bedazzling capability his brain has got through the story of light. So without much ado, Aakaash, please take the stage.
Hi everyone, can you hear me? Can you hear me? Okay. Nice. Wow. Thanks very much for such an introduction. I'm just kidding. It's all him. I'm very glad to be here in this forum. As Siddharth mentioned, I spoke here last time, and this is my second time. I mean, I was 25, I'm 26. This reminds me of a Crazy Mohan joke. I don't know if you've heard it. Can you hear me? Oh, okay. Yeah, I should be a bit closer. Yeah, there's a Crazy Mohan joke that goes like, hey, எனக்கு என்ன வயசு தெரியுமா அப்படின்னு கேட்பான். இன்னொருத்தன் சொல்லுவான், என்ன ஒரு 27 இருக்குமா அப்படின்மா. ஒன்று சேர்த்துக்கோ அப்படின்னா, என்னது 271 அப்படிம்பாங்க. And the it's just 1 year, but this seems like a long time, and I can see how much the Varamahira Forum has gone from strength to strength. And it's been very special, this forum. And we are running on the clock already, so let me just begin the talk. So since you're here, you already, I presume, know the title of this talk, which is The Story of Light. Light is something which we all know, and since the day we are born, we have some kind of an inbuilt intuition regarding light, and that intuition serves well for our survival. But that does not necessarily mean that we are born with all the knowledge of light there is. The physics of light is something that's very unintuitive, and it took literally centuries for us to figure out a simple thing that's just bouncing around all day. And today we'll look at some of the story, and some fascinating tales, and some peoples, and a little bit of physics. Those who don't like physics don't need to worry about anything. I'm not going to thrust any equations in your face. Well, maybe I'll just show you, but I don't need you to understand them. So when you're talking about a story of someone or something, you have to go at the beginning, and you have to start from the beginning. And when it comes to light, the beginning is the beginning of everything itself. And that's the birth of the light. It's the Big Bang. Before telling you the story of the birth of photon per se, let me just give you a quick word on what Big Bang is. So in the early 1900s, or in the late 1800s, we knew a little bit of physics, and we knew the laws of physics to some degree. And the foremost physicists of that time thought that the universe was a static one. So Newton gave his theory of gravitation, which I'm sure you would have heard. It's just very simple. If you just take two masses, and if you just keep them, and then you just let it go, can you hear me? Yeah. So with time, the mass just starts attracting, and they just clump together. Now, this theory meant that if the universe was finite, and if you give enough time, let's say that this room is the universe, and the gas in this room are the particles in the universe. And if you give enough time, all the particles will attract with each other. And after many years, millions and billions of years, everything would clump together, and you'll just have one object. So this was a bit troubling, and we saw that maybe it's not really the case. So also it was an elegant thing to assume that universe was infinite, and that the universe was always there. But in 1915, we know that Einstein gave his theory of gravity, which is much more accurate than Newton's. Newton's gravity is true only to some extent. If the mass of the objects is much higher, then Newton's laws just break down. But Einstein's laws, as far as we know, is very accurate and holds true. So then you can ask the question, okay, if I have two masses, they will just clump together. Now, if I ask the question, what will happen if I put all of the universe and ask the question, what happens then? Well, so after 1915, his theory was published. It was confirmed by Arthur Eddington in 1919, and Einstein became world famous all of a sudden. In fact, even after his special theory of relativity, he was not that famous, but after 1919, he really became world famous. And then people read about his theory, and they understood it. And there was a Catholic priest called Lemaitre, and Lemaitre tried to answer this question, which is, what if I put all the contents of the universe and ask the question, what happens in the future? Lemaitre found out, to his surprise, that the universe must expand. And he wrote to Einstein, and Einstein told, what bonkers are you talking? This must not really be true. And he himself took up his paper and pen. He started working out, and then to his surprise, he found that indeed universe must be expanding. But the popular thought at that time was that universe must be static. So in order to make the universe static, in his theory, he introduced a term, and that's called the cosmological constant. You don't need to know what that is. Just know that he just forcibly put in a term to make sure that the universe looks static. But then in 1929, Hubble, who was a famous astronomer, discovered that the universe was indeed expanding. And then Einstein hit his forehead. He told, me putting in that term is the biggest blunder of my life. And then till now, it's true that it is a fact that the universe is expanding. And now if you ask the question of, okay, the universe is now expanding, now what happens, what would have happened later? What happens if you play the movie backwards, right? So now everything is expanding. Well, before in time, everything must have gone nearer to each other, right? And there must have been one point whereby all the particles in this universe was compressed to a single point. And that point is what we call the Big Bang. The moment we start the clock from that point is what we call Big Bang. And the name Big Bang, how it came about is a little bit funny. There were still scientists who were not convinced about this crazy thing. How can a universe get created? What nonsense are you talking? And there was this famous astronomer called Fred Hoyle. And in one of the radio shows, I believe, mockingly he told, oh, you think the universe starts with a Big Bang? And then the name just caught on. And it became a technical term, which we still use. And in 2019, as far as we can tell, all the evidence points to the fact that Big Bang would have happened, or at least something very similar to what we think Big Bang is must have happened. So that's the beginning of everything. And the first minute, what happened in the first minute? Well, at t equals 0, universe gets created. And I'm putting everything in quotes because we are not sure what really happened, and one can never be sure because we don't have any experimental evidence to assertively say with any surety that only this happened. So the universe is in quotes because we don't know if there is only one universe. There can be many, which is not accessible to us. And gets is in quotes because we don't exactly know if the mechanism with which the universe got created. And the created is in quotes because universe may, after all, not have been created. It may have been that the universe expands, and after a long time it starts contracting and comes to a single point again, which we call big crunch, and then again the Big Bang happens, the universe starts expanding, and this cycle goes on and on and on. Maybe that is also a plausible scenario. And exclamatory mark is because maybe it's not a surprise that the universe was created. Now this treads on philosophy and not really mathematics or physics because, again, we don't have any experimental evidence. And this reminds me of a phrase from the Hitchhiker's Guide to the Galaxy, where Douglas Adams begins like, in the beginning the universe was created, and this has made a lot of people very angry and been widely regarded as a bad move. But at t equals 10 power minus 35 seconds, to those who are not familiar with scientific notation, you don't need to worry what that is. So when I say 10 power something, if it has a minus sign, I just mean that it's 1 over 10 with so many zeros. So if I say, for example, 10 power minus 2, it means 1 over 100. There are 2 zeros that follows 1 in the denominator. In any case, 10 power minus 35 is an extremely small amount of time. And at this time, with the fundamental constants that we know, we can say to some degree of surety that the physical laws that we know must have come into existence. And that's just an argument based on physical constants. And at about t equals 10 seconds, we have particles. And the particles, when I say particles, I mean protons, neutrons, electrons, neutrinos, and all other everything except light. And I must give you a warning that even though I put t equals 10 seconds, it's not really accurate. I mean, the early universe is a mess. You have the primordial soup, everything just happening. Particles are getting created along with its antiparticle, and then when a particle and an antiparticle smash, they annihilate into 2 photons, and you have light, and you have all sorts of crazy things going on. But at t equals 10 seconds, you have a lot of particles, and at about t equals 100 seconds, all the particle and the antiparticle that was created, they merge, and you have light. So when a particle and a particle collides, they turn into 2 photons or 2 light. When I say photon, I mean light. Light and photon are interchangeable. We'll come to later what a photon is, but at about 100 seconds, the universe is just full of light. And we have the first ever stable race of light. Again, I've taken some poetic license. There may have been stable rays even in the first 10 seconds, but after the 100th second, you have light, which is filled with in the universe. And now we have an era of light. So also the universe is very, very hot at 100 seconds. The temperature, if you can imagine, is about 100 crore degrees Celsius, which is very, very huge. We can't even imagine that. And we must also remember in the meanwhile that the universe is expanding, right? Because we know that universe is expanding even right now. And the contents of the universe now is not just light, but you also have particles like protons, neutrons, and neutrinos, and dark matter, which we don't yet know what it is. But we are guessing that it must have been there way earlier because evidence suggests so. So all these particles are also swimming around. And now the light just completely dominates the universe because the light is very, very energetic. The temperature is 100 crore degrees Celsius, if you can imagine. So the photon just it's a rowdy. It just wanders through, and if all the protons and neutrons just give way to photons. And also, it's the photons which are very, very high in number. In other words, it's the light which is very, very high in number. For every one proton or one neutron, you have 200 crore photons. Then you can imagine how much of a majority photon is. But again, you must remember that the universe is again still expanding. And as things expand, things start to cool down. And once we cool down a little bit, what happens is at about 56,000 years after the birth of the universe, the light, the energy content of the light, and the energy content of everything other than light equals. So this is when in the tug of war between light and matter, you have an equivalence. Now, both are pulling and pushing with the same strength. So now photon does not dominate as much as it did in the first 56,000 years. And now, when I said tug of war, it's almost literally like that, because you can just imagine this room, even though we cannot see, there are gases, and all the gases are just pulling and pushing each other, and it's a mess. And light has this ability to just go at its own speed, and it's also very highly energetic. So the particles all just push and pull each other. It's just like a tug of war. And at about 3,70,000 years after the birth of the universe, the light finally loses the battle. In other words, the light is not as energetic anymore. Now, it cannot push and pull around particles as it wishes. So if you want to form an atom, you may have known that the most primitive atom is hydrogen atom, right? And hydrogen atom has a proton, and it has an electron. Now, if you want to form an atom, first, the electron which is swimming around must get married with the proton, and it must get captured around the proton, and you have the atom. But earlier, the light that was around was so energetic, it never allowed the proton and electron to combine. It just because the energy was just so much. But at about 3,70,000 years, light has cooled down, and now the electron and proton can merge and form the first stable atoms of the universe, right? So, and now they combine to form the hydrogen atom, and we have the first ever stable atoms of the universe. Again, this is just a poetic license. Even earlier, hydrogen atom would have been formed, but immediately it would have been destroyed by the photons, and it would have just been on and on. But after 3,70,000 years, we have a steady increase of atoms in the universe. And now, I remember you telling that the photons and the matter just pull and push each other, right? But at 3,70,000 years, no, the photon does not have any more energy, so there is no pushing and pulling anymore. Now the universe has expanded so much that light can now freely propagate to free space. So now light, all the light that was there, now just escapes. You may ask, escapes into what? I would say escapes into universe. So there is no more pulling and pushing, and is now free to propagate throughout space. And this light, which escaped about 3,70,000 years after the birth of the universe, is something which we can detect even today. And it's called the cosmic microwave background radiation. It's called CMBR. It was discovered in 1964 by two gentlemen in America. In fact, they had this huge horn antenna, which they wanted to find the CMB radiation. And when they were looking for the signal, they had some kind of noise constantly, and they didn't think this is CMB was the noise. In fact, they were thinking it was the pigeon droppings that was giving the signal. But they found out that it's not. It's in fact the universe's remnant light which is coming. And they got the Nobel Prize for discovering that in 1964. But anyway, so this is what light, the story of light in the sense it's in its infancy. So now let's fast forward by about 1,377 crore years. And I've put that number because that's the age of our universe. I mean, compared to crores and crores of years, 3 lakh is nothing. So this is almost the age of the universe. But in the meanwhile, we have Milky Way, which is our galaxy, and it forms just 20 crore years after the birth of the universe. And after Milky Way is formed, the sun forms around 900 crore years after the Milky Way is born. I mean, Milky Way formed very early, just 20 crore years, but sun takes about 900 crore years to get formed, because the stellar ignition, it's just what happens. Statistically, you can never say why. And the Earth forms about 10 crore years after the sun is born. So how the planets form is that you have this sun, which is not really the round yellow gas fire ball of fire that you imagine. When it first formed, you had all of these other objects which was just circling around it. And I want you to imagine a disk, the center of which is sun. And in the disk, you have all the particles that are just revolving around about the center, which is the sun. And with enough time, the particles in the disk get together. Whichever the massive particle is, it gathers mass. And with enough time, they become planets. In fact, if you look at the solar system, all the planets are in the same orbital plane. And that's because all the planets are formed in the same disk, the primordial disk when the sun was formed. This is how Earth must have looked when it first formed, not the blue-green ball that we know. And the oceans apparently formed just 10 crore years after the Earth was formed, which is fascinating. Now, when I talk about light, we talk about light only with respect to us, because we are here, we are talking about light. So it's important that we also have a look at life and light. Now, undoubtedly, light must have played a role but we have no doubt that it played a role in shaping of life. But light may have also played a role in the creation of life. So how can you answer this question? I mean, what is the first sign of life? Well, experimentally, we can't time travel to 4 billion years and then see when the first life started. The only way that we have, because I mean, the Earth formed about 450 crore years earlier. And the earliest life is just about 100 crore years after the Earth is born. But we have no idea how the Earth was back then. We don't know the landscape, we don't know accurately the chemical composition, and we don't know where the continents were. Continents would not even have been there, at least the way it is right now. You'll have volcanoes, and you have magma, and you have all sorts of crazy stuff going on Earth. But the only window that we have to see life about 4 billion years ago is this crystal, and this is called a zircon crystal. And even though it looks big, this is just about the size of a hair's width, just 0.1 millimeter. Maximum it goes to 0.3 millimeters. It's a crystal which is extremely hard, and it can withstand heavy temperature and heavy pressure. In fact, if it's formed inside a rock, it can even outlast the rock in which it was formed. And we have excavated the zircon crystals that were formed 400 years ago. Now, inside this crystal, there are atoms that are trapped in its crystalline structure. Now, one thing that we know for sure is our life is carbon-based, right? So one of the things that you can do is look for carbon atoms inside the zircon crystal, which was about 4 billion years ago. And most of our zircon crystals, the earliest signs of life that we have is from this area called Jack Hills in Australia. I don't know why it is there only in Jack Hills. Perhaps the conditions were conducive for its preservation. Okay. Gobu says there are some samples in India. You mean it was found in India? Okay, nice. Right, and the next thing is photosynthesis. Again, photosynthesis is a very, very important reaction for life to happen. Now, it is entirely possible that life would have evolved without photosynthesis, but in our Earth, it seems that photosynthesis has played an extremely important role. So the evidence of the first photosynthesis that we have is just after about 20 to 30 crore years after the first life. This is a paper, I think it came out in the 1990s, and it still stands true as far as I can tell. I'm not an expert in this field, but seems like this is not yet disputable. And we have this thing called cyanobacteria, which would have been possibly the first microbial organism which uses light and gives out oxygen. So you need an organism. If you and I we are breathing oxygen, and there must be some source, right? So even the creatures that lived before us, way before us, did consume oxygen for living, and this is an important step in the evolution of that. And with time, all these bacteria, and then there may have been other bacterium which gave out oxygen, and with time they just gave atmosphere the oxygen. Before that, the atmosphere did not have any oxygen at all. There may have been traces, but very minuscule. And this is called the Great Oxidation Event. Now, the graph that you see is the atmospheric oxygen content, and you see that from the beginning, the graph is very, very low. So the red is the maximum possible and the green is the minimum possible. So the truth lies somewhere in between the two, but you can have an idea. You see that after about 3 billion years, it just starts shooting up. So exactly, we would not be here if not for the photosynthesis of the earlier organisms. Again, as I said, maybe life would have evolved some other way, but we and I definitely would not have been sitting in TVA today evening if not for that light, which helped the bacteria to give oxygen to the atmosphere. Now that's just light, and then light would have helped millions and millions of species in one way or another in its evolution, but we don't know many of them, and it's humanly impossible to talk about all of them, and let alone research. But we can talk about ourselves, the humanity, and light, and how that goes about. The first thing that comes to mind is fire, right? So who first used fire? So which human used fire? It's a trick question. Most probably humans did not use the first fire. In fact, it's very much possible that the ability to make fire would have predated the emergence of Homo sapiens, but definitely our ancestors, our biological ancestors, various other types of hominids, they would have gradually understood fire, and there is very little doubt that the hominids moved out of Africa without knowing to use fire. So it must have happened well before us. In fact, the recent paleontological evidence suggests that Neanderthals have used fire much more efficiently and much more earlier than Homo sapiens did. Now, does this mean the Neanderthals knew to start fire? That we cannot say, because we do not have evidence for that. Interestingly enough, this image that you're seeing, this is a campfire which was lit about 1 lakh years ago. It is charcoal, and you can find this only where natural fires cannot occur. And you have many sites like these. And what is interesting is, you find signs like, so in the past 1 lakh years, there have been 2 phases where Earth was experiencing colder climates. And during when the Earth was cold, we do not find any fire sites at all. You would imagine that you need fire only when things are cold, right? But it seems as if that Neanderthals have used fire only in the warmer climates. Now, this leads us to believe, which may not be true, again, it's a speculation, but it may be that Neanderthals did not know to create fire, but they used it. It may be that there is a climate gets dry during warmer period, and you have forest fires, and you have many other natural sources of fires. You have geysers, and it may be that Neanderthals obtained fire from that, and they used it. There is a movie called Quest for Fire, where the Neanderthals, they don't know how to make fire, but they try to maintain the fire. In 1981, people did not know if that was true or not, but no, I have not seen the movie. Seems like an interesting movie. You should check it out. But it seems like that movie may have been true after all. And I mean, like many things, it could have happened in stages. Right now, our closest biological relative, who are chimpanzees, chimpanzees are very interesting. So they understand fire very well. In fact, chimpanzees understand fire to the extent that they are not afraid of it. Almost all other creature gets afraid of fire. At least once it gets hot and once it gets burnt, it understands that it should not, approach it. But chimpanzees seem to know how fire spreads and how fire works. So in fact, there have been studies made of chimpanzees in natural wildfire environments, whereby the chimpanzee is cool as cucumber. It does not waver at all. Up until the fire comes just tens of meters near, the group just starts and slowly walks away to an area where the fire does not spread. So it does not mean that chimpanzees know how to use fire, but we see that this is a very important step if we want to utilize fire. And this I presume, or the researchers say, we presume must have happened about 4 lakh years ago. And slowly, we would have gained the knowledge, and through the wisdom that's being passed on generations and generations, we knew how to use fire. So that's for fire. Again, if you want to talk about light, you can talk many things which we in fact we don't even know what we don't know if you want to really track the history of light. But let me jump to civilization and talk about lenses. When you say light, the one thing that comes to mind is optics, and when you say optics, one thing that comes to mind is lens. So what is the earliest excavated lens? The earliest excavated lens is the one that you're seeing, and it's called the Nimrud lens, and it was we believe it is made around 750 BC in the Neo-Assyrian Empire. So the Assyrian Empire started about 2800 BC, and slowly it gained power. And by the time of the Neo-Assyrian Empire, which is about 900 BC, it was the largest empire in the world up until that point. No Greek, no Latin, no Romans. It was the Neo-Assyrians who ruled the world. It was the biggest empire. And apparently they were the first to use iron as a weapon in their warfare. And they were extremely tactical, and they are also said to be extremely cruel, which is debated. They may have not been more cruel than any other ruthless kingdoms. But anyway, so this was made in that time. So this is a convex lens. This is a plano-convex lens. By plano-convex lens, I mean one side of the glass is just flat, and the other side just bulges out. It's a plano-convex lens. But was this made for optical purpose? We do not know. In fact, this may well have been for decorative purposes. In fact, you find many glass articles along with furnitures and many other things which look fancy, that it may not have been for optical purposes. It's possible, maybe, but we can't say for sure. Now, what is the earliest mention of lens? So the first mention of lens comes from the play The Clouds by the Greek dramatist Aristophanes. And here in the play, Socrates and Strepsiades talk. And he says, have you ever seen at the druggist place that beautiful transparent stone with which they kindle fire? And Socrates answers, you mean glass? So it seems that during that time, people have used quartz glass, which is a crystalline silica, not the usual glass. So they've used that to start fire. Even now you can see kids using the magnifying glass. You go to balcony and you keep the magnifying under the sun, and you keep a paper underneath. The paper will just catch fire because all the light gets focused to that single point, and it's just too much energy for the paper to resist. And this is the Roman statesman called Seneca. And he mentions that the hollow spheres can be filled with water, and the water will act as a magnifier. But this does not seem to be widespread. for some reason. I mean, we have various other accounts that say that if you are a Selvandar in a Roman Empire, if you get old and if you can't see, you just have your slaves read whatever that you want to do. And one of the reasons why eyepieces may not have been that widespread is because very few people knew how to read. Most of the population was illiterate. In fact, in the Egyptian Empire, 99.9% of the people are believed to be illiterate. The hieroglyphs were not for laymen. That was one of the reasons why it was very, well, it was very hard to decode hieroglyphs. One of the possible reasons may be that we just had the Rosetta Stone to decode and no other evidence. Had the language been widespread, we would have had other sources to decode hieroglyphs from. But anyway, the theories of vision is a curious topic. Many people were interested in this. Can you hear me now? Much lesser? Can you hear me now? Okay. Seems like I have to. Yeah, it's fine. Right. So now we have the theories of vision, where many Greek philosophers were interested in this topic, and we shortly go through one by one. And the first is the Democritus, and Democritus was a philosopher who put forth the atomistic view of the universe, by which he meant either you have atoms or nothing else. So everything in this universe is either made of the most fundamental entity called atom, and then you have empty space. The etymology of atom goes like, so tom means cleaving or cutting, so you have vasectomy, which means you're cutting, and means the negation of it. So atom means one which cannot be cut, which is the most fundamental entity there is. So he was in fact, one of his famous quotes is, everything is, the universe is made of atoms and empty space. The rest is just opinion. So, and then Epicurus in 341 BC, who lived from 341 to 270, proposed that when you see an object, the material inside the object gets detached from it and comes and reaches your eye. So if I'm seeing you, it means that the molecules of your body, whatever part I'm seeing, if I'm seeing your hand, leg, hips, head, everything, so the atoms from all of those organs just detach from your body and is hitting my eyes. Now you can ask, okay, if that happened, then what happened to the primary body in the first place? Shouldn't that be empty? So he suggested that no. When I'm seeing you, your atoms are coming to my eyes, but the air around you is automatically filling the gap with which the atoms that reach my eyes are vacating. Now this may be a little bit bonkers, but so was everything. So Plato suggested that light consists of rays which our eyes emit. So he suggested that when I'm seeing you because my eyes is like a torchlight. So the light comes out from my eyes, it hits you, and then it's not as if the light gets bounced back to my eye back. So just like how you feel an object using your hand, so if there is a ball, tennis ball, you reach out your hand, and if you close your eyes and if you grasp the tennis ball in your hand, you will know what the object is. He proposed that there is a similar kind of a hand in your eye which reaches out, touches the object, and tells you what that object is. Now again, this theory has its flaws, to which we'll shortly come to. And then Plato, again, and Plato and Aristotle were strong proponents of this theory, which said that your eyes has an invisible hand which can feel things, and that's how your brain knows what you are seeing. And this will not be proven wrong for 1,000 years until the Islamic Golden Age comes, where you have many people, you have an absolutely brilliant scientist doing experiments to disprove this. So the optics in ancient India, again, as I told, atomism is something that was prevalent. And we also have that in our schools of philosophy. And in fact, there have been complex philosophy to which I'm not really an expert. but this is something which is surely worth studying. It's told that the Vaisheshika school had complex theories pertaining the working of optics. And I think they believed the world is made of 4 elements, of which Tejas was fire. And one of the theories was that our eyes are made of Tejas atom. Everything is made of only of these 4 entities, and our eyes are possibly made of this. And Shushruta, being a surgeon, was also an ophthalmologist, and he seems to have said that it's not the light that externally makes us aware. It's our brain which processes the image which we see. So that's exactly what really happens. And we have Varaha Mehra, upon whom this forum is named, and in his encyclopedic work called Brahma Samhita, so he writes this sloka. I don't know Sanskrit, so I'm not going to explain this. Perhaps Gopu is a better person to do this. But what this sloka means is that the multicolored rays of the sun being dispensed by wind in a cloudy sky are seen in the form of a bow, which is rainbow. So this, to my knowledge, is the first ever scientific description of rainbow in our literature or anywhere else. And in fact, in his Brahma Samhita, there are about 40 mentions of the word rainbow. And for some reason, he does not like rainbows. In fact, he says that if the solar disk be cut across by a rainbow, it indicates something untoward is going to happen to the ruling chief of the country. In another instance, he says the rainbow appearing in front of kings, starting of an expedition, brings about their defeat. Rainbow pati nallada solli paakavilla and the 40 instantly. But anyway, I think this may be the first scientific. This is exactly what really happens, to which we'll come to. And then we move to the Islamic era, which is called the Al-Kindi. And he is in fact perhaps the first great philosopher of the medieval Islamic era. So he in fact learned a lot of Greek philosophy, and he translated it to the Islamic world. And in fact, it was Al-Kindi who first introduced the Indian numerals to the Islamic world and to the Christian world. So his De Aspectibus, which is a Latin translation of his Islamic work, had a strong impact on many of the Islamic and the Christian scientists of that time and down the generations. And Al-Kindi used many of the geometric constructions. Algebra was not yet there. Everything was just pure geometry. And he used that to explain things like vision, reflection, and refraction, and the burning mirrors, why do rays get focused, and so on and so forth. And but he was a primary supporter of the Aristotelian and the Euclidean way. So, but the Aristotelian view, if you remember, is as if your eye has an invisible hand and it reaches out and it feels. But he was not convinced that, because let's say that you see a circle, right, and you stand in front and you see a circle, it appears as a perfect circle. But now if you move to the side and if you see the circle, no, it does not appear as a circle. It appears as an ellipse, some distorted way. Now, if there was an invisible hand which came out from your eye and felt the shape of the image, then it must still be perceived as a circle, because it is indeed circle. Now, if you close your hands and if you feel a tennis ball, it's going to be only spherical in shape. It's not going to turn into cube. So Al-Kindi knew there was a flaw in this logic, and he preferred Euclidean theory more than the Aristotelian theory. And again, he also made some changes to the Euclidean one, which let us not bother ourselves. And we come to Al-Hazan, and he is perhaps the father of modern optics. So in fact, he was the first to suggest that the vision happened because light reflects objects. Right, light gets reflected off an object, comes to your eye, and you see it. He was the first to suggest that. And in fact, again, after Shushruta, if Shushruta indeed had told that, he is the second person to have told that it is our brain which processes the image after the image hits our eye, our retina. And he was also perhaps the first proponent of the modern scientific method, which is that you make a hypothesis, and then you make a prediction, and then you go out, you do an experiment, you check whether your prediction is right or wrong, and then you decide whether the theory is true or not true. And having that spirit, he decided to check if the Aristotelian theory of light is true or not. So just to remind you again, Aristotelian theory meant that there is some kind of an invisible sensory which comes out of your eyes, feels the object and tells your brain. So his experiment was very simple. So he just had a screen, and then he had a wall, and he just put a hole in the wall. And he had two lamps, one above the hole and one below the hole. And now what he did, he switched off one lantern, and he had only one lantern on. So when you switch on, you see a spot on the screen. And then now he switched this one off and switched that one on. So now the spot was formed on a completely different place. So this seems to suggest that our brain is just getting the information whatever it gets. Nothing is coming out of our eyes and feeling or nothing of that sort. So this he also proved that light goes in a straight line. So if you see this, he drew a line between the spot where the image falls, the hole, and the lantern, and he had a straight line. And this is perhaps the first instance where the rectilinear property of light was confirmed experimentally. And this just threw out the 1,000-year dogma of Aristotelian theory, and just opened a new gateway to see optics. And in the meanwhile, he was also the first to invent the pinhole camera, because when he did this, if you have a wall, and if you have a small hole, even in your house, you can buy aluminum foil, and if you cover your windows, and if you just put a small hole, and if you take your veshti and you keep it, you will find that all the image outside the journal comes and falls invertedly, and that's nothing but the pinhole camera. So he was the first to invent the pinhole camera, which would be very useful later in the advent of optical instruments, including telescopes and so on. And then we come to Descartes. In fact, Descartes was perhaps the greatest French philosopher there was in the modern times, and he is credited to have started the modern philosophy. You may have heard the famous term which is ego cogita ergo sum, which means I think, therefore I am. So he told that the reason that I'm here, just the fact that I think would just suffices for the fact that I'm here. And he was also the first person to link algebra with geometry. Earlier, they were just two separate fields. And by the way, Descartes was also the first guy to use x, y, a, b, and all those variables that you use in the school. So if at all you were finding a person to scold who invented this x, it's Descartes that you have to blame. And so his interest in optics was to geometrically see what the law of reflection was, and he treated light just like tennis balls. In fact, if you take a tennis ball and if you throw at a wall, if you do not have any gravity at all, the ball will go and hit and come back just like the way a light would do in a mirror, against a mirror. And he also discovered the law of refraction by himself. So to those who remember their high school, you may have heard of Snell's law. In fact, Descartes discovered the law 16 years before Snell did. I will tell you what this law is in a short while. And Descartes was also the first to decode rainbows mathematically. So he found that the light has to hit at about 42 degrees, exactly 42 degrees, if we have to see rainbow. In fact, you see, so this is the ray that comes from the sun. It hits the raindrops and it comes to your eye. This angle between the sun's ray and the reflected ray must be 42 degrees if you want to see a rainbow. He did not know why it is 42 degrees, but I mean, he did not know the intricacies of the molecular stuff that's really happening. But just using geometric optics, he tried and deduced this. And then we come to the law of reflection, which is very simple. So you see a ray that's coming in, and it hits, and it just bounces off. This is a mirror, and the law of reflection says that this angle is the same as this angle. Now you can ask why. Well, that's a very easy question to ask, but it's not as straightforward. In fact, thousands of years ago, the hero of Alexandria, who lived from 10 to 70 AD, he asked this question. And this guy is one of the greatest experimenter of his time. And in fact, he's credited with many ingenious inventions. So he's the first to invent a steam-powered device. And he also invented the windmill, which we know. It's just perhaps the first ever construction was done using his design. And he also invented a vending machine back then. And the vending machine was to give out holy water. You put in a coin and you get a holy water. So he also was interested in many plays, stage plays, dramas, and props. In fact, he shares this with Leonardo da Vinci. But Da Vinci was also interested in, well, he was an artist first and foremost, but his idea of flying objects, be it an aeroplane or helicopter or whatever, would have stemmed from the fact that he was working as for a prop for a drama. And Hero of Alexandria goes the same way. So he proposed that the law of reflection is the way it is because light wants to travel the least distance. In fact, if you propose that, okay, I have my light, I have my mirror, this light must touch this wall at least once, and it must come back on this side. And if you put in the condition that the distance traveled by the light must be the minimum, you will get angle of reflection equals angle of incidence. And that's just a simple geometric fact, but he proved it using geometric means. And we come to a law of refraction. Reflection is when light goes, hits, and comes back. Refraction is when light goes and goes through the material. In fact, when light goes through a material, it will bend. And how much does it bend was a question that was unanswered for many centuries until the 1600s when Descartes and Snellius, both of them figured out why. In fact, they got the law, but they did not know why. So, in fact, this is the Snell's law. So this is an equation, you don't need to worry what that is, but they just found this equation empirically. So they did the experiment, they got the value, and they found this relation exists. They did not know why. So the question for why this relation is true was answered by Fermat. He, again, is one of the greatest French mathematicians of all time. And he was actually not a mathematician by profession, he was a lawyer. And but he made a lot of important he did work which started new fields in mathematics. So I think he was one of the foremost to use probability theory. Even geometry and those things were already there, but you may know him with this famous theorem called Fermat's last theorem, which is nothing but a Pythagorean theorem. The statement of Fermat's last theorem is that the Pythagorean theorem is not true for any number greater than 2 in the power. So you have a squared plus b squared equals c squared. Now, instead of the squared, if you have any number other than 2, then that's not true. That's a statement he made, but we could not prove it up until just up until late 1990s. We could not prove. Andrew Wiles from Cambridge proved that. But anyway, so he asked this question: why does the light bend the way it does? The equation which I showed you the previous slide, why is it true? So he proposed that light takes the least amount of time to travel in the medium it does. So when light, let's say that you have a glass slab and light goes inside the glass slab. Now in air, light is going like this because this path is what light takes least amount of time. But once it goes inside the glass, it bends, and now this is the least amount of time it takes to go from point A to point B. So this is highly non-intuitive, but he proved it. He proved it mathematically. And yes, so mathematically we just derive this law. And then comes the Talavar Newton. He is, in fact, the greatest physicist since antiquity and since everything. In fact, I personally would rate him more than Einstein. But he is unparalleled in his prowess. And you should listen to Siddharth's talk, which I presume was in 2018, February, something like this, 2017? 2017 November. He gave a talk on Newton, on the Principia Mathematica. Alexander Pope, who was one of the greatest poets of the 18th century, told that nature and nature's laws lay hidden in night. God said, "Let Newton be," and all was light. In fact, so much was Newton's contribution that we would not be here if not for Newton. At least the world will be a completely different place if not for Newton. So he invented calculus, he discovered the laws of motion, he discovered gravity, and then he calculated the speed of sound as in a side pastime. In fact, he even invented calculus just to prove that there was a rival of his called Robert Hooke, about which I'm shortly talk. So he contested the fact that the laws of Newton does not give planets to have elliptical orbits. So he went and then he already had done the work, but that paper got lost somehow. He had done that way earlier, and then he again from his memory just did what he wanted, and calculus was born. And he was just 25 at that time. Just amazing. And besides all this, he also pioneered in optics. So the origin of color. So people had various different ideas about color, and the primary one was the color was given by the object. So up until then, light had nothing to do with color. So if the chair is red, that's because the chair is red. The redness is because of the chair and nothing else. That was the prevalent thought. But in 1666, Newton started investigating through prisms, and he found that white light, which is sunlight, gets decomposed into various colors. And not just that, so each color bent at a different angle. And this is very fascinating. In fact, the color of light is something which people already knew. Of course, they knew rainbows existed, but they did not realize that white light can just be decomposed into all these colors using a simple glass prism. So this led him to conclude that color comes from light, and color is not a property of the object per se. It is the light which gives color. And Newton explains this in Word of the Newtons. So he says that I might add more instances of this nature, but I shall conclude with this general one, that the colors of all natural bodies have no other origin than light itself. That they are variously qualified to reflect one sort of light in greater plenty than another, which is bang on right. If you see an object red, that is because light is falling on that object, and it just reflects back red more than it does any other color. That's why we see that object red. It's fascinating. And he also does experiments where he uses minerals, mineral stones like bise and minium, and those minerals, if you in a dark room, those materials will be of whatever color of light that you shine upon them. If you shine blue light on that mineral, it will look blue. If you shine red light, it will look red. So this again led to the conclusion that color originates in light and not in the objects. And again, he publishes a small treatise called Of Colors, which he would later expand to his perhaps the second best treatise in physics next to Principia. And also, as a side, since he knew that when white light goes, or any sort of light goes through a material, it splits. If you have a telescope, right, so you're getting light from a distant star, and when that light goes through the magnifying lens and it comes to your eye, because from the prism experiment he knew that the light split, he wanted to build a telescope which did not have any refraction. It only had reflection. So he built this reflecting type telescope. So if I want to, so let's say that the star is here. So the rays of the star comes from this side, and it hits a concave lens which tends to focus light, and it hits to the second mirror, and this mirror comes to our eye. So this is an ingenious invention, very simple, but nobody had thought of that before. So the world's first reflecting type telescope was constructed by Newton in 1668, and in fact Newton could see 4 moons of Jupiter, which no one else could up until that point. And also, he could also see the crescent face of Venus, which nobody had seen before. His friend, Isaac Barrow, showed a replica of his telescope to his friends, and they were so impressed that they decided to show the telescope to Charles II, who was the King of England at that time. And immediately next year, Newton becomes a member of the Royal Society. So, and also a reflecting type telescope is something that's very easy to build. If you have just a piece of mirror and cardboard, you can do it even in your home. So, வீட்டில் பண்ணீங்கன்னா கோட்டைக்கு போய் எடப்பாடியார்கிட்ட காட்டுங்க. You will get into the Royal Society or whatever there is here. So yes, we come to Newton's Optics, which is the second best treatise of his work. In fact, he did not publish this earlier, even though he had done all the work. This may possibly have to do with the fact that he did not want to face Robert Hooke and his criticisms. And Robert Hooke, he dies in 1703, and Newton publishes all the work that he had done earlier in 1704. And it's a monumental work, and it paves way for, again, the modern optics, the most modern optics. And then we have light as a particle. Newton presumed that light was a particle. So he thought that when the white light goes inside the prism and it separates, he thought that the various different particles are traveling at very different speeds inside the prism. And that's why they have different colors. That's what he thought. And also, the reason why Newton thought light was a particle was because he was very fond of assuming natural objects to be point-like particles. Even in his Principia, if you go through, the point mass and the materialistic point assigning to things is very prevalent. So it's perhaps natural for him to consider light as yet another discrete particles. But the theory that light is made of particles ran into some troubles. It could not explain, for example, this process called diffraction. What is a diffraction? Well, so if light goes through a hole, light bends. We don't know why it does if light was a particle. So if you assume light was a particle, we could not explain why this was so. In fact, this is true even for sound waves. If not for diffraction, you will not hear, the guy in the next room, you will not hear him scream. Because if, let's say that you are in the hall and your friend was in the bedroom, and if you shout his or her name, in fact, the sound wave that come out of your mouth bends around the door and it goes to the next room. That's the diffraction of sound. And similarly, this is something that's true for any kind of wave, and this is true for light. And there is something called interference, which again I'll tell what that is a little bit in a little while. This people could not explain if light was a particle. And there was something called polarization, which again you did not worry. This property of light could not be explained if light was a particle. So then comes Christian Huygens. So Huygens was a Dutch. He was born in 1629, and he lived for 65 years. And he is widely regarded as a very major figure in the scientific revolution in the late 1600s. He was the one who first discovered the rings of Saturn, and he discovered the moon, its moon Titan, which we now speculate there may be some life. So as an inventor, he invented the eyepiece to the telescope which we keep, and it's called Huygens eyepiece. And most importantly, he invented the pendulum clock. And he invented this in 1600s. Up until 1900s, 1930s, his pendulum clock was the most accurate timekeeping machine that ever existed in the world. And then, of course, electrical and electronics came about. So he was interested in optics, and he was the first to suggest that light was a wave. So he published his treatise of light, and he also was well, up until that point, mathematically people could not explain reflection and refraction if light was a wave. If it was a tennis ball, you could explain, right? But people could not come up with a mathematical theory up until that point. But Huygens, being a smart guy that he is, was able to do that. So he introduced this concept called wave front, which means the wave as it goes creates a new wave each and every instant as it goes about. So that's what light does. And then even though he gave his theory, people were not entirely convinced that it was true. People still believed Newton to be true. And then came Thomas Young. So Young is said to be the last man who knew everything. He was a complete all-rounder. He was actually a physician, and then he made contribution study of solids, physiology, language, musical harmony, and Egyptology. In fact, when the Rosetta Stone, which is the famous stone which has the Greek and the old hieroglyphs and the new hieroglyphs, that was excavated during the Napoleonic Wars, there was a competition between the French linguist Champollion and Thomas Young as to who was going to crack the hieroglyphs first. And the British took away from the French the Rosetta Stone, and Thomas Young had the Rosetta Stone in his he could avail it as he pleased, but Champollion only had casts of the Rosetta Stone. But very closely, Champollion beat Young to cracking hieroglyphs. Thomas Young was very close, else he would have been credited with the cracking of hieroglyphs. He had many feathers in his cap. So he at the age of just 14, you can just see how much. I'm not going to read out all the languages. I don't even know these languages. I don't even know these languages existed. Like Amharic, which I checked out was Ethiopian language. He seems to have been a complete all-rounder. And he devised this experiment called the double slit experiment. And it's very similar to the experiment which I told earlier. So you have a lantern here, and you have a single slit. So from this slit, light goes to the next two slits, which are equidistant from this slit. And now, from both of these slits, light is just going and hitting the screen. Now, if light was particle, what you would imagine is, let's say that you are firing bullets. Let's say this is a machine gun, and you are firing bullets all over these slits. With enough time, you will find a bunch of bullets here and a bunch of bullets there, because it's just straight to the hole. That's what you would expect. But what Young found was he found an interference pattern. There were dark and light spots consecutive to each other, and this could be explained if and only if light was a wave. Let me quickly show you an animation. So you can see that from both the slits, light is coming out, and light is a wave, which means it's going up and down. So from the one slit, a light is coming and it's going towards the screen, up and down. And from the other slit, you also have a light which is coming out and it's also going up and down. And when both these lights meet, either depending on what condition they meet, if both are going up when they meet, you have a bright spot on the screen. But if both are going down, you again have a bright spot on the screen. But if both cancel each other, then you have a dark spot. So this can be explained if and only if light was a wave. And this was a tremendous discovery. And by now, people realize that light must be a wave. And we next come to another of the interesting properties of light, which is very, very difficult to measure. It's even a triumph that we were able to measure this, which is the speed of light. So the first person to have tried to measure the speed of light was Galileo Galilei. And he went to a mountain, and there were about a gap of about 1.5 miles from him and his assistant. And the deal was that once he switches on the lantern, he will see how much time it takes, and the delay would correspond to the speed of light. And when they did this experiment, it was just too instantaneous. In fact, they could not find any delay at all, which meant for him to conclude that either the speed of light is infinite, or it's at least 10 times faster than the speed of sound. Because speed of sound, from the distance, they already knew what the speed of sound was, because all it takes is to detonate a bomb 300 meters away and see it arrive 1 second later. But light was just too fast to do that. Now, this gentleman, who was a Danish called Ole Romer, so he tried to measure the speed of light in a very smart way. So Jupiter has 4 moons, and the closest of the moons is called Io. And this was actually discovered by Galileo in 1610. And Romer knew that if you have 3 objects, right, like a moon, a planet, and sun, you're bound to have eclipse. Right? And since the speed of the moon around the Jupiter is fixed, the eclipse must happen periodically. right? So you know the duration between one eclipse and another. That's something that you can calculate, and you already know. So he exploited the fact that the Jupiter and Sun, Jupiter is going around the Sun, and Earth is going around the Sun. Both are not going at the same speed, right? So there will be instance when the Earth and the Jupiter are on the same side of the Sun, there will be instance when they are on the opposite side of the Sun. So his trick was to exploit this fact and see the eclipse on both of these occasions. If I show you an image, this may be more clearer. So you see, this is Jupiter. So now the Earth and the Jupiter are on the same side as the Sun. So now you can see the eclipse. The moon disappears and the moon emerges back, and you can find what this is, right? And you know eclipse happens regularly, so you know when the next eclipse is going to happen, and you know how Jupiter goes around the Sun. That also you know. And now when the Earth and the Jupiter are on the opposite side of where the Sun is in between, and now again you see the eclipse, but now the light from this eclipse must travel an extra distance, which is the diameter of the Earth's orbit around the Sun. So this extra distance means that light arrives later than it did the previous time. So this delay, and also we also know the distance of Earth to Sun. So we know this distance. So exploiting this fact and seeing how later the eclipse occurs, he tried to find the speed of light, and it was astoundingly accurate for his time. So he found that the eclipse happened about 22 minutes later than it must have happened. Now we know that the light from light from Sun reaches Earth about 8 minutes. It takes about 8 minutes. So if that's just the radial distance, right? If you include the next another 8 minutes, that's about 16 minutes. And with the equipment of his time, he found this to be 22 minutes. And this is almost exactly twice the distance between Earth and Sun. And he calculated the speed of light to be about 220,000 kilometers per second, which is really close for his time, if you ask me. The real value was 299,000 kilometers per second. He was close at 220,000 kilometers per second. And this is amazing. And the reactions to Romer were a bit mixed. Then the then director of the observatory, who was Cassini, and Cassini he made extensive studies of Saturn's moons. If you remember, there was a mission to moon that was named Cassini and Huygens, and in 2017, I think the mission got ended, and they crashed the spacecraft into Saturn's atmosphere. It was named in his honor. So he was not really convinced about Romer's observations, and Robert Hooke, who was alive at that time, he could not believe that light can be this fast. It was just impossible for him to even fathom or realize. And however, Newton, I don't know if he favored Romer's observations. I don't know if this is because Robert Hooke opposed it, but and also the young Edmund Halley, after whom the Halley's comet is named, even he agreed with Romer's observations. However, even though at that time there may have been some criticisms, his observations paved way to the fact that the speed of light was finite. Up until that time, there was even a question whether speed of light was finite or not. But now that it was established that it is finite, and many other people did many more experiments to accurately pin down the speed of light. In fact, right now, we define a meter with respect to the speed of light. We do not measure the speed of light with respect to meter. It's the other way around. We have gotten so accurate with our atomic clocks that we define the meter using the light's speed, and not the other way around. That comes to the question, what is light? Well, I'm not going to go into extreme details as to the mathematical and the physical formulation of light, but let me just give you a small historical taste. So James Clerk Maxwell, so he was perhaps between Einstein and Newton, he was the most influential physicist there ever was. In fact, before Maxwell, there was electricity and there was magnetism. And in the meanwhile, many people were doing many experiments like Ampere, Oersted, Faraday, and others, and they had separate independent results. But Maxwell realized that electricity and magnetism were two sides of the same coin. And he formulated everything into just a bunch of equations. And those equations now can just be written in 4 lines. And the 4 equations that you see here, plus gravity, is everything you will ever experience in your life. Electromagnetism and gravity is what life is. And every natural phenomenon that's going to happen on Earth is just because of these 2 forces. And just these 4, all these equations were derived independently. Experimentally, the first equation says that if you have charge, there will be electric field. And the second equation says that if you have a magnet, bar magnet, right? Bar magnet has a north pole and a south pole. The second equation says that if you cut the bar magnet, you will never separate north and south. If you cut, this piece again forms a north-south, and this piece forms a south-north. So you can never isolate a pole by itself. That's what the second equation says. Third equation says that if you change magnetic field, you will get electric field. Fourth equation says if you change electric field, you will get magnetic field. It was actually an achievement of unparalleled sorts. That I think this is perhaps the first time people realize the beauty of elegance in physics. That so much phenomenon can just be written in 4 equations. And till now, all of the 20th century physics was driven purely in search of this elegance and what we call beauty. And that everything can just be explained using the 4 equations. In fact, Einstein, when he visited Cambridge, where Maxwell was, his host told Einstein that, Mr. Einstein, you are standing on the shoulders of Newton. But Einstein replied, no, I'm not standing on the shoulders of Newton, I'm standing on the shoulders of Maxwell. Because his first paper was on the theory of electromagnetism, or electromagnetism of moving bodies, which is where he published his special relativity. But anyway, Maxwell was a towering figure. And there's something intricate about these equations, that you see these 4 equations, they are independent, as I told you. And if you substitute one of the equations into another, now all these 4 equations are true independently, okay? Now if you substitute one equation into another, you get another equation which must also be true because the first 2 equations were true, and the new equation is nothing but an equation of a wave. And people did not know what that wave was. And it's just there right in front of you. You have a mathematically, to describe a wave, you have a mathematical function, you have a differential equation that tells what a wave is. And these equations spit out that wave equation. But people did not know what that wave was. And now, by the time Huygens and Young did their experiments, people knew that light must be a wave. So Maxwell, in 1873, took a giant leap and asserted that the wave which his equations are spitting out is nothing but light. Now, for the next 10 years or so, people around the world tried to experimentally verify if light was an electromagnetic wave. And at last, 14 years later, in 1887, a gentleman called Hendrik Hertz, he experimentally verified that light was an electromagnetic wave. So he did that using a simple experiment. So you see there is a gap here. Oops. So there is a gap here, right? And there is a gap here. So this has circuit in it, and this does not have any circuit in it. You can just connect an ammeter or a current meter to see if there is any current. Once you activate this circuit, a spark forms between these 2 balls, and immediately a spark was also found between these 2 balls. So this was a clear evidence that light was an electromagnetic phenomenon. But what is an electromagnetic wave? So here there is an animation. So electromagnetic wave has both electric stuff and magnetic stuff. So the blue thing that you see is called an electric field. You don't need to know what that is, but know that it is a quantity called electric field. And similarly, B is called the magnetic field. Now both, they choreograph in such a way that if you remember in the Maxwell's equations, I told you that if you change electric field, you will get magnetic field. And if you change magnetic field, you will get electric field. Light is nothing but a self-sustaining machine where electric field changes, and because the electric field changes, the magnetic field changes, and because the magnetic field changes, electric field changes, and this is a self-propagating machine, and it just keeps on going and going till the end of time. So this here, the X that you see, that's the direction of the light. So if light is going this way, the electric field and magnetic field change usually perpendicular to the direction of the light. And this we call a transverse wave. But anyway, so we now mathematically know what light was, which is an electromagnetic wave. So a word about the weirdness of light. So now comes Albert Einstein. So I mean, there is very little, the introduction is needed as to who Albert Einstein is. But Einstein and Newton have a fascinating parallel that they both just shook the physics from its foundations, and both gave a theory of gravitation. So when Newton gave his theory, his was the most perfect theory at his time. And when Einstein gave his theory, his was the most perfect, even superseding that of Newton's. And both contributed immensely to the understanding of light. And Einstein had a miraculous year in 1905. It's called Annus Mirabilis, which means a miraculous year. He published 4 papers, and all 4 papers changed the history of physics in 20th century. And the first paper was on Brownian motion, where he talks about a particle suspended in a liquid and how the particle moves. You must remember that in 1905, the existence of atoms were still in question. People were still not sure if atoms existed and if solids was made of atoms. But Einstein's paper put the last nail in the coffin to the fact that indeed material is made of atoms. And the second paper is called on the motion of electrodynamic bodies. I forget, but anyway, that paper is the special relativity paper. So where he completely changes the nature of space-time as we look. In fact, a special lecture is needed to devote time to tell what special relativity is, because special relativity is not really difficult to understand. It's a little bit tricky, but I did not want to do this because it will run out of time, and I won't do justice to special relativity if I do that. So that was the second paper. The third one was the mass energy equivalence, where he famously told the most famous equation of the world, which is E equals mc squared. And the fourth one, these are not chronological, by the way, the fourth was published first. And the fourth one was on photoelectric effect. So this told us about the nature of light. So what is photoelectric effect? Well, so photoelectric effect was already observed earlier, but nobody was able to explain why. And let me tell you what that is. If you have a metal, and if you shine light on the metal, all of a sudden you see electrons coming out of the metal. Now we don't know why. So there was a caveat with this, that no matter how strongly you shine light on the metal, it will be the brightest lamp you can find. If you shine that, the metal did not give an electron. But even if you used a single ray of light of higher frequency, then electron just came out. And this was very perplexing. So Einstein provided a way out of this. Before that, in 1900s, there was something called ultraviolet catastrophe. I'm not going to go on into what it is, but there were a discrepancy between experiment and theory with regarding to radiation, light radiation from hot bodies. Max Planck suggested that if light came in discrete packets of energy, then we can go around this problem. And in 1900, he suggested that. But in the photoelectric effect paper, Einstein went one step ahead and asserted that light is made of discrete particles. And those discrete packets of energy is discrete particles of light. And this was again monumental, because you must remember that in 1905, the fact that light was a wave was established firmly. And this is just going back to the Newton's days. And imagine the courage it must have taken for Einstein to put forth this proposal, to going back to 1600s. And many couldn't believe this, again, because they knew light was a wave. But Robert Millikan So he did an experiment in 1923 wanting to disprove Einstein, but he ended up proving Einstein. So he found that photoelectric effect was true. And in fact, Einstein got his Nobel Prize. Many would think it was for his relativity, but no, it was for the photoelectric effect paper. That was why he got the Nobel Prize. So this comes to the question, is light a particle or a wave? Well, I must say that light is both a particle and a wave. So the fact that we cannot put light into one of these baskets is not really a fault of light, but it's fault of the English language. Because we, as humans, have evolved to perceive things and put into either a light basket or into a particle basket. But mathematically, we know perfectly well what light is. And in fact, in the 20th century mathematics, which is called quantum field theory, we exactly know what light is. But the fact that we cannot say whether it's a particle or a wave is a shortcoming of the English language rather than physics. And it's not just that. In fact, everything is both a particle and a wave, not just light. Even you and I, who are made of protons and electrons and neutrons, even we are wave. If you probe at sufficient energy. So the confusion of this goes to our perception and our understanding of quantum mechanics, but mathematically we do not have any problem in understanding what light is or what matter is. And then we come to the last personality of the evening, which is Sir C.V. Raman. He was very interesting, and he was born in Trichy in 1888, and he was actually a stellar student. When he was just 11, so he passed the matriculation, and when he was 13, he finished the +2 equivalent of his time. And when he was 19, he finished masters, and he was a gold medalist at that. And then he was waiting what to do, what should I do, what should I do. And like many people of his class and his age and his upbringing, he took to taking a government job. But from age 19 to 29, he was leading a double life. So he was both a scientist and a government official at the same time. And so he was also so extremely good at his work that people expected him to clamber up the rungs very fast and one day become even a member of the Viceroy's Council, which would be equivalent to the finance minister post of today. But it was not to be. So in 1927, Ashutosh Mukherjee, who was the founder of IACS in Calcutta, Indian Academy for Cultivation of Science. So Ashutosh Mukherjee was also not a scientist, but he was a High Court judge in Calcutta. But he was so much into science that he started an association which devoted its time entirely to pursuit of physics. So he became a member of, I think he became a director of Calcutta University, and he made funds and he made Raman an offer to come and study there as a pilot professor. And Raman, even though the salary was less and he was looking at completely no perks which a government job would offer, he gladly took the job and he went for professorship. And everybody was mad. Why are you doing this? You will become, a finance minister in a few years. But Raman's heart was elsewhere. So before going into the work of Raman, let me just quickly tell you what frequency is to those who don't know. So if a wave is said to have high frequency, then they are packed closer to each other. So you see the blue here. So it means it happens more quicker. So if you imagine the blue propagating this way and hitting a wall, since it's more closely packed, so more of the wave will keep on hitting the wall. But if you see the red, it's not closely packed, it's loosely packed. So if the wave is closely packed, we say it has high frequency. If the wave is loosely packed, we say it's low frequency. And there was a gentleman called Compton. So he did an experiment in 1923, and the experiment is very simple. So he took X-ray, which is light, and he shone it on an atom. And the X-ray hit the electron, and it bounced back at some other angle. So what Compton found was that since we established that light was a wave, X-ray is a wave, and X-ray has some frequency, right, which has it's packed in some way. And after the light hits the electron, it gets reflected, and when you observe the reflected X-ray, its frequency has not changed. So this was this is called, which we call it elastic scattering. But anyway, this was something which was not observed earlier at all. And this was a time when quantum mechanics was starting to brew. It was not yet fully understood, but it was in the air. And this Compton did with X-ray, right? Raman wondered what happens if instead of X-ray, I used visible light. What happens? So in other words, what happens when light goes through a material? Does the frequency of the light change or not? That was the question. And the seed for this thought happened when Raman was coming back from England in 1921. He went to England in 1921, and there's a famous story where Raman apparently enters into a lecture where Rutherford is lecturing, and he quietly went and sat in the last row. And Rutherford and Raman had not met before, but Rutherford stopped his lecture and asked, "Why, Professor Raman, come to the first row and have a seat?" And then after the lecture, Raman asked, "How do you know that I'm Raman?" "Well, why? Because of your turban, of course," he told. So all along, Raman had very good relationships with scientists abroad. And in 1921 was his first trip, and he was coming back. And while he was returning, he was looking at the sea, and he was wondering why the sea was blue. Lord Rayleigh had given an explanation stating that the sky is blue, and at that point people understood why sky was blue. That was because of the light scattering. So he just stated that because the sky was blue, the sea is just reflecting the sky, so sea is blue. But Raman was not really convinced by this. So being Raman, he always had a pocket spectroscope on his bag, and in the ship he started thinking about it, and he was observing the sea light, and he was taking the spectrum of the light and so on. And when the ship stopped at Aden, which is in Yemen, to restock, he quickly went and he wrote a letter to nature. And then from Aden, it was again a ship voyage to Bombay. And when he went to Bombay, he again hurriedly went and he reported his thoughts to nature again. And this kindled his interest very much because he got a clue of what could happen when light goes through a material. So the discovery, so again, this does not, he works for 5 to 6 more years. And Raman and his students at the association, so they work extensively to see what happens when light goes through a medium. And so one trouble that happens when light goes through a medium is, let's say that you have a medium and you send in light. So the light that comes out need not necessarily be the same light which you sent in. The materials sometimes have a property called fluorescence, whereby just because light went through, it will switch on and it will emit light by itself. So it's not the same light which you took in. And that took a lot of patience to avoid that or to nullify that. And after a lot of meticulous study, at last on February 28, Raman observed that when visible light goes through a medium, it changes its frequency. It was completely different from what Compton had seen. And in fact, I must say a part of enthusiasm why Raman was vigorously doing this was because in 1923, Compton got the Nobel Prize. So Raman knew that there is some fish here to smell. So and then in 1928, when he knew this, he immediately knew the breadth of this achievement. And also February 28 is also considered as a National Science Day in India because Raman discovered this on February 28. And there was also Krishnan, his student. He was a PhD student, and he was not there at that time. So people often say that Raman stole the work of his student, but that's not really true. So it's true that officially the spectrum was taken by his student, but it was Raman who pushed in that direction, and who even in US universities, for example, there have been cases where the advisor tells you what to do, and you are still a graduate student and you don't know entirely what you are doing, and at the end you get some marvelous result, and it may even be a Nobel Prize worth result, and not always you are also credited with that achievement. There have been cases where the student was also got the Nobel Prize. There was this incident called Robert Wilczek, where he was just a graduate student. He published a paper along with his advisor when he was 21, and the work was so monumental that they had to give the Nobel Prize for all the names on the paper, which was he and his advisor. But back then that was not the case. So this scattering, where the light changes its frequency after going through a material, is called Raman scattering. And it's now used all over the world. We use it very detailed to know the nature of materials, and also to make more efficient lasers and many other countless stuff. And he, of course, was hailed by one and all, by the physics community. And Rutherford mentioned his important work in the presidential address in the Royal Society. He was the president back then. And also, Raman was also, he also knew that this was a big thing. So in 1928, he made the discovery. So in 1929, he booked a ferry, thinking that he will get a Nobel Prize. So he booked the ferry in June, July, and the ferry was to start in December. So he did not want to go to a situation where he may not get ticket. So he put a ticket for him and his wife, thinking that he will get a Nobel Prize. So he and his friend, daily they will go and get the newspaper and see whether if any announcement has been made for the Nobel Prize. If he did not get, he'll just toss away the newspaper and just walk. And that year he did not get the Nobel Prize. Next year, you think Raman would learn, but he again booked the ferry, thinking he will get the Nobel Prize. And in the meanwhile, Sommerfeld, who is a very great physicist, he made a tour to India, and he visited Bangalore, he visited Calcutta. Primarily, he came to Calcutta because of Raman, and he writes everything in Calcutta is beautiful except for the bathroom. And he comes to Bangalore, and he comes to Madras. He delivers a lecture on quantum mechanics in Presidency College, and he writes everything in Madras is good except for mosquitoes. And then he goes to Sri Lanka, and then he continues his journey. So when he comes, Sommerfeld is in the Nobel Committee, and he tells Raman that his work is so monumental that he will be nominated for the Nobel Prize. And again, the next year, Raman again books the ferry and daily goes and buys the newspaper, and this time he is awarded the Nobel Prize. And the 1930 Nobel Prize goes to C.V. Raman. And in the Nobel lecture, he seems to have gotten a standing ovation, and but just one person was a bit sore that he mentioned his dear friend from the jail, and that person was a British ambassador, and that dear friend from the jail was Gandhi. And that instant, Raman realized that it's not just he who is sitting there, but he's there representing all of the Indian people. And it's really true that it was Raman who put the Indian science on a global map. And if not for Raman, there is very little doubt what would have happened. If in fact, if you now go to any physics department, I can say with some surety that it's either populated by Bengalis or by Tamils. So Raman was in Calcutta, and he was also a Tamil. I think that may have to do with this, but he started as cultivation of science. And of course, India has its own rich history of physicists like Meghnad Saha and Homi Bhabha and Alladi and others. But the real missionary started only here. And this is the picture where Raman is he is the physics, and the next to me I forgot the names, but the other gentlemen are the rest 5 people who got the Nobel Prize for their contributions. And if one has to talk about light, one can just keep on going, but I thought I will finish with Raman. So that's it. I think I hope I've done some justice. So, and it's also time. So let me stop here. Thank you. Yes. So if you have any questions, please do ask. There's a mic here, and just feel free to ask anything. Yeah, they're running a little late, so we'll just have 1 or 2 questions.
Raise your hand, I'll come to you.
Yes.
That was a very enlightening talk, not pun intended. So,
Yes.
So my just this is a small question. So I just used to hear about this lighthouse paradox.
What is it?
That when a lighthouse is when light comes from one place to another.
Okay.
So the farther distance it is, when it hits the second place, it hits it with superluminal velocity. So light it's traveling faster than the speed of light. So can you explain on that?
Right. Sure. So you're asking that in the lighthouse you have a bulb which is rotating, right? It is spitting out light, and just like if you took a valakmare or if you took a stick and if you revolve it, the stick will move at some point, right? But now in the lighthouse, what happens is the bulb is rotating. Once the light leaves the bulb, light just keeps on going straight. The light has no business of what the bulb is doing. The bulb just gives out light and just keeps on going straight. Because the bulb is rotating, it just keeps on shooting straight lines of light as it revolves. It does not really change the speed of light. Speed of light is the same, no matter how fast the bulb rotates. It's something which we cannot change.
Thank you very much for enlightening discussions on various aspects.
Yep.
But my question to you is the beginning of the quantum theory, which you are enlightening. Can we take it? It starts from the era of C.V. Raman or beyond that?
So C.V. Raman's actually quantum mechanics was born from 1925 to 1926. In a remarkably short period of time, Heisenberg, Schrödinger, and various other people, they put forth quantum mechanics was done by 1927. Raman, he discovered this effect in 1928, and his effect is primarily a quantum mechanical effect. Classically, the frequency of a light never changes. The change of frequency of a light is purely a quantum mechanical effect when it goes through a medium. So quantum mechanics does have a role to play in explaining the Raman effect. Right. Can I have one more? If any? Yes.
Great talk. Thanks for
Thank
that.
you.
Now the laser, the beam of laser,
Yes.
laser beam, they also have properties of cutting or pushing things, don't they?
Yes. So light has energy.
Okay.
And if light has energy, it can impart that energy to other things, right? So in fact, there are these ideas called solar sails, which mean that you just need to have a sail and the light from the sun hits that and it pushes. So technically we call this radiation pressure, and it's a very true phenomenon. In laser, it's even more prominent because you are focusing so much of a beam into so little a width that it just hits and it goes through the material. In fact, the laser does not spread at all. If you took your laser pointer and if you pointed it towards moon, when it falls on the moon, I mean, if let's say that you take a torchlight and you hit on the roof, right? You will see a circle of light, right? The circle is already 2 to 3 meters big. But if you take a laser and if you shot at moon, in the surface of the moon, there will be a light only of about 10-meter diameter. So laser is so constrained that all the power is concentrated in a single linear fashion. So when it hits a body, it pushes or it even melts the material very easily. So that's why it happens.
Any more? Done?
Yep.
Okay.
Okay, thank you very much. Again.
Thanks, Aakaash, for a actually very delightful lecture with several aspects of history. I think some of us knew about Newton, perhaps Descartes, but to bring in Varahamihira, especially, and of course Alhazen and Christian Huygens and all these other characters, Thomas Young, for example, that was a excellent tour of the history of light. So thank you very much for a wonderful lecture. Like last month, we have the father of the speaker in the auditorium, but he's a little more shy to come to the podium. So I request a very good friend of his, Mr. Soundararajan, to hand over the small token of our appreciation to Aakaash for his lecture.
Thank you so much.
So the next month's lecture is going to be on biology. It's about food and its nutrients. Dr. Arun Kumar of Coimbatore Biotechnology is going to talk about it. He's going to talk in Tamil, I think. Unavin Uirottam அப்படின்னு அந்த nutrients of food பற்றி அவர் பேச போறாரு. So I look forward to seeing you all next time. We've got your names and email addresses and so on. If any of you are interested, our lectures are we have a Facebook page, we have a WhatsApp group. You can contact one of us. We'll add you to the group if you want. Please welcome any friends you want to come to the group. We have a discussion group, not just for events, but also for just generally discussing science. Tamil Heritage Trust does a monthly lecture every first Saturday. So the next Saturday, first Saturday, we'll have a lecture at RK Convention Center. It will be about Manohar Devadas. He'll be talking about A Tale of Two Cities, about Madras and Madurai. So that will happen at RK Center. And next month, the fourth Saturday, we'll have next Varahamira Science Forum lecture on the nutrients of food. Unavin Uyirotam by Dr. Arun Kumar. Thank you.